So now that we've talked briefly about what you can control and what you can't, let's start taking a closer look at what you can in fact control. So we'll see that you can control things splitting with splitterators, you can control combining with collectors, and you can control some aspects of the apply phase, although not a whole lot, by the way in which you can allocate the number of threads that are used in the common fork join pool. Now, just as is the case with sequential streams, the splitting, combining, and pooling mechanisms of parallel streams are often invisible. What that means is that you can take what you get out of the box and it works perfectly well. As we've seen before, Java collections have predefined splitterators that can be used in conjunction with some other stuff to create parallel streams. So here you can say we have the collection interface, and this has a splitterator, and that splitter out of the box does something very specific, and then it can be overridden and customized by either concrete collectors that come out of the Java collections framework, like array list and linked list and so on, or you can actually take control of splitting things up if you so desire. And that's especially important when you make your own collectors for your own collections. You can see here that the parallel stream factory method that's defined out of the box in collection, the collection interface, goes ahead and uses the stream support.stream factory method using the splitterator and passing in the parameter true. And true just means go ahead and do all this processing in parallel. Java also comes with a bunch of predefined collectors, non-concurrent collectors in the collectors utility class. So here we have things like toList, toSet, toMap, grouping by, partition by, and so on. And all these non-concurrent collectors work for sequential streams, of course, but they also work for parallel streams. We're not going to talk right away about how non-concurrent collectors work with parallel streams, but we'll come back to that a little later, probably next class, perhaps, if we get that far. And that'll give us a chance to really look into how parallel streams does its processing and the difference between parallel collectors and concurrent collectors and non-concurrent collectors work in that context. The actual secret sauce for doing the computations, of course, will be provided by the common fork join pool, and that will be used to run all those intermediate operations on the chunks of data that are spit out by the splitterator. And especially if you have a parallel splitterator, you'll actually be running those things in parallel in different threads and different cores in the common fork join pool. All of this stuff can be customized one way or another. So this is the part where you have to be aware of what's possible with the streams framework in order to be able to control its behavior. So you can define your own splitterators. Before, we talked primarily about TryAdvance, but we're also going to talk about TrySplit. So TryAdvance is used to process the elements sequentially for both sequential and parallel streams, because once you reach the minimum size in the parallel splitterator, at that point, TryAdvance is used to do all the other processing that may be available. TrySplit is the new thing we're going to focus on in our parallel streams discussion. And of course, that's going to be used to partition the elements up to the chunks. You've already written a TrySplit method as part of your unsynchronized array splitterator, your array splitterator that you wrote. And that's one of the things where you have to be very careful to make sure that you're doing the computations correctly. Otherwise, you'll end up with strange results. Demonstrating once again the incredible utility of things like unit tests, where if you have the unit tests, they will find these problems and keep you on the straight and narrow. If you don't have the unit tests, then you'll just get strange results and be mystified as to why your program is doing odd things. There's also the collector interface, as we've talked before, that has a bunch of methods in it. It's got essentially 5 methods that are used to define the mutable result container that the stream is collected into, an accumulator method that accumulates the elements into that mutable result container, a combiner method that's used for non-concurrent collectors in the context of parallel streams to be able to merge stuff together very cleverly. And then there's a finisher, which can be omitted in some circumstances, that's needed if you have to transform the mutable result container elements into some other data structure when you want to return a final result. Now, the one thing we haven't talked about before, because we've talked a bit about splitterators, we talked a little bit about collectors and so on, we haven't talked about managed blockers. And they're intended to be used to control the few little pieces of the apply phase that you have any influence over. So it turns out that what you can use a managed blocker for is you can actually use this to automatically create threads that will go into the common fork join pool. So you can expand the size of the common fork join pool automatically under certain circumstances, most particularly if other threads that are running in the common fork join pool will block. Now, we'll talk a bit about this later when we get into more of the details of how the common fork join pool works. But the common fork join pool really would like to do run to completion non-blocking operations. That's really what it wants to do if it had its druthers. But there are certainly circumstances where you can't avoid blocking. And probably the best example of this is if you use parallel streams to do any kind of I/O operations. So reading from disk, reading from the network, and so on. And if you're using it for those purposes, then there's going to be blocking. And the moment that there's blocking, then you have the whole issue of what do you do if all the threads in the common fork join pool are blocked waiting for I/O to complete? And the tricky part there is there could actually be other work to do. And those threads that are blocked aren't actually consuming cores at that point. And so if you're not careful, you'll end up massively underutilizing the available processing resources on your multi-core processor by having all the threads blocked waiting for I/O to complete. So what you can do is you can use this thing called a managed blocker, which will help to expand the size of the common fork join pool invisibly to you, the programmer. It takes care of these mechanisms under the hood. And that way other threads will be created. They can then start doing work that's not blocking, so they can use the cores to make forward progress. And then over time, if you have a bunch of threads that are created dynamically to handle these blocking operations, then over time, if they remain unused for a period, the common fork join pool will go ahead and shut them down and reclaim the memory that they would use. So it's basically sort of a control system-like mechanism to keep the amount of parallelism that's usable at a fairly constant level. And then once there's not as much processing to be done, it'll go ahead and reap and delete or remove, destroy the threads that are not currently being used. So it'll bring it back down to the default size of the common fork join pool. I'll talk a lot more about that later. We're not going to talk, we will definitely talk in this course about the common fork join pool, and I'll explain it from the point of view of how you program it using parallel streams. But if you really want to know all the gory details about the common fork join pool, you'll need to go take my companion course next semester that's going to talk about this in more detail. So that's just a quick overview of some of the things that can be managed and controlled and customized through splitting, combining, and pooling with parallel streams. And then we'll explore some other dimensions of this in other videos that come later in the course.